So I'll tell you about contracting high-dimensional tensor networks. This is work primarily done by Johnny Gray, who actually spoke in the last year's version of this meeting. So some of you may know him already. He's a research scientist in my group, and we have a very fruitful collaboration together. Okay, so I'll just start with one slide about the promise and also the failures of tensor networks in some ways. I was just reflecting on this when putting together this talk. So general tensor networks beyond DMRG and MPS are almost 20 years old now. I remember the excitement when the first talks and papers started appearing on PEPs, for example. And at that time, the original premise was that somehow we discovered the correct way to write down low-energy states of physical systems. And this was the way it would be. And that was, of course, really exciting. And to some extent, that vision has proved true, particularly in the formal sense. Tensor networks are a great way to reason about states, different types of order. They're more formal statements to express in what sense they represent classes of physical states, for example, in the area laws. And there are many explicit constructions of model states in terms of tensor networks. But from the viewpoint of numerical modeling, the reality is really a little bit less positive. I mean, certainly in one dimension, DMRG, as it always was, is this ultra-powerful technique, which just essentially solves almost everything. In 2D these days, using PEPs, one can do pretty good simulations, but they're nowhere near as good as DMRG is in 1D, right? I mean, they give you sort of good accuracy, but certainly not, you still want some more digits of precision. An example I show here is from some fermionic PEP simulations we ran recently in some other context on the 2D Hubbard model. And you can see that with fermionic PEPs, as you push to large bond dimensions, I mean, you get to about 1% of accuracy, which is certainly not bad for the Hubbard model. This is a difficult doping point, 1x doping. But to fully resolve the physics of the Hubbard model, you really want 0.1%. That's the kind of accuracy you expect from DMRG, and so one is certainly not there yet. And in 3 dimensions, I mean, there are almost no calculations, right? So nature is, of course, 3-dimensional if we're talking about representing all of nature. So in that sense, tensor networks haven't really fully lived up to their promise. So why is that? Well, that's partly because tensor network algorithms in higher dimensions are just complicated in many sense of the word complicated. Now, the first operation you encounter when you're dealing with tensor networks, unless you're dealing with mirror, is the problem of contracting it. And in one dimension, there's only one way to contract a tensor network. Well, actually, there's only one correct way, right? If you don't contract it that way, you're doing something stupid. But immediately when you go to 2D, there's already many different types of algorithms that people talk about. And in some ways, in 3 dimensions, there's even more diversity that you can imagine, although in practice, very few things have been implemented. And so really, my talk is really about exploring this space here. And there are essentially a few challenges that we'll face. One is that at least there's a reputation that implementing tensor network algorithms in higher dimensions is complicated. I mean, it's just a matter of doing some work and doing some hard work, but I mean, that at least that is, in principle, one problem. The second is that there's obviously a large diversity of things that you can do, so you have to sort of answer the question of what should you do, like what's the best thing to do, perhaps. And in higher dimensions, it's actually hard to verify that what you're doing is good, because there are very few benchmark results. There are not many things that you can exactly contract, or at least, and there are not many sort of models that give you sort of where you know the exact answer. Okay, so essentially today we'll try to address or begin to address these questions. And I'm going to address them in the context of finite tensor networks. Many of the things I'm talking about, you could imagine in the context of infinite tensor networks with respect to the unit cell of the infinite tensor network. But today I'll focus really on the finite setting. OK, so the talk is basically 3 pieces. First, I would just talk about just implementing some manual TensorNet contractions just to get a feeling for what's going on there. We identify that a particular type of manual strategy, which we call higher order CTMRG, is probably like the best one that we can think of, at least, to do in 3D. That's sort of simple to implement. Then the second part is about sort of optimizing over a space of many, many tensor network contraction algorithms. This is applicable to arbitrary graphs, although this talk is really in the context of regular 3-dimensional graphs. This work is on the archive. It's been there for a long time, in fact, as this paper on hyper-optimized compressed contractions. And then finally, I'll talk about how we can construct instances of things that correspond to large tensor network contractions, but where you know the answer. And we'll introduce this concept of hidden loop tensor networks to answer this problem. OK, so let's just first start with just implementing tensor network contractions manually, but in 3 dimensions. And we can think of a few, sort of just extending from the 2-dimensional literature, some types of contraction algorithms that we could use. There's essentially 2 classes. There's sort of methods which know that there's an edge to the system. So boundary type MPS or corner transfer can be thought of as knowing that there's an edge as well. And in these algorithms, when you compute the isometries, the things that do the compressions and the contraction, they relate systems that change by size, by size 1, by 1 row or 1 column. And then the other sort of family methods are these sort of RG methods, and these RG methods sort of don't start from the boundary. They just start essentially from the middle, and the isometries then relate systems of size related by a factor of 2. So they sort of double the system size. OK, so analogs of these types of things can, of course, be formulated in 3 dimensions. And at least to my knowledge, and this could be incorrect, people can correct me if they've implemented these things, but as far as I know, these things haven't really been done in finite tensor networks, so we have to implement them. OK, so what do some of these algorithms look like? Well, one can do this sort of RG-style algorithm. This is a figure taken from the infinite version of this algorithm. So you can see you take these tensors and you do this renormalization type mapping where you go, in this case, from a cube down to a single tensor, and you insert lots of isometries to do this compression. So it's some type of coarse graining type transformation. Because it doesn't make use of the boundary in the finite tensor network, you expect these algorithms to have a high scaling because they start from the middle where all the tensors have lots of legs. One of the efficient things about these types of proposals is that the isometries are computed independently. So we have these pairs of tensors, they're all compressed independently from each other, and so there's some efficiency from that type of strategy. OK. An example of the other type of strategy is something that knows that there's a boundary, and we're going to consider explicitly in this talk just the ones that know that there's a corner. So the idea here is that you compress from all the faces, sort of one by one. So you go sort of in the x direction and compress in one face, the y direction compress in one face, the z direction compress in one face. And then the compression that we compute, usually when people talk about corner transfer, it's some fixed point type approach because you're doing an infinite system. But in a finite system, you have to compute the projectors at each compression step. They're all going to be different. And here we use essentially the same style as in HOTRG, where you just take pairs of local tensors and then compute the compression or the isometries between them. Okay, so it's just, since we're doing a kind of finite CTMRG, but with higher order TRG type isometries, we just call this HOCTMRG. OK, so we contract in from each face, and we compute the isometries HOTRG styles. And there are many other things that one can imagine. For example, you can imagine a direct analog of boundary methods in 2 dimensions, where you just take one face of the tensor network and you push it all the way through to the other face. I mean, we've also tried that, and that actually doesn't work very well. So I actually won't show those results. OK. So the first thing we can do is just sort of analyze the scaling. It turns out there's many terms in the algorithm, so it's a little bit complicated to analyze. So each of these squares here corresponds to different terms in the finite algorithm. And there's a scaling with respect to the original bond dimension and a scaling with respect to the renormalized bond dimension. And so, for example, a term here would be chi to the 11, d to the 0. And a term here would be chi to the, 10, d to the 1. And then depending on whether chi is, what value you choose from a renormalized bond dimension, different terms will dominate. It turns out that in HOTRG, if you choose chi to be like d squared, this term dominates. If you choose chi to be like d, this term dominates. In either way, you can write the scaling down as chi to the 11. Okay, so this is the scaling of the 3D finite HOTRG. The HOCTMRG is similarly got lots of terms. What's D? D is the dimension. So we're contracting a tensor network where the tensors have an original bond dimension D, and then they're compressed to when you contract them to bond dimension chi. Yeah. Okay. So there are also this similar thing with different number of terms. If we take the sort of chi-dominated term, then the scaling is sort of chi to the 7d. If you look at 2D algorithms, they have scalings that look kind of like like this. It depends exactly how you do it. Let's say chi cubed d to the 4. So that gives you some idea of the relationship between 2D and 3D methods. Okay. But it's significantly lower than just TRG to HOTRG because this method knows that there's a boundary. OK, so we can just apply this then to a three-dimensional model. This is the 3D icing model. We apply at sort of the critical temperature. Of course, this is a finite system, so it's not really critical, but at the bulk critical temperature. And then one can look at the accuracy. So this is the error. Roughly speaking, this is the derivative of free energy with respect to the bond dimension. So it's representing how well the thing is converged, but you can take it as the measure of the error. There are a few things you see, right? So as a function of time, TRG is up here. This is because it has this terrible scaling. The HOCTMRG is obviously much better. And you can see, because of the better scaling, these numbers here represent the bond dimension that you're using, the chi, and so you can go to a much larger chi. And this red is some other method, which I didn't talk about, so you can ignore it. OK. So you can reach, indeed, very small errors, 10 to the minus 7 in a reasonable amount of time. So that's just to show that it's possible to do these things. They're not really so bad. Now, how is this compared to 2D? So one way is to compare the sort of types of contraction errors in the 2D icing model and the 3D icing model. So this is a slide I took from someone else, I think Marita's slide deck. And you can see that in the 2D icing model, near the critical point, the type of errors one's talking about, the free energy, are on the scale of 10 to the minus 6 to 10 to the minus 8 using a variety of contraction techniques. Actually, it doesn't change too much with the different techniques. And here, with chi equals 24, with the HOCTMRG, one's talking about sort of 10 to the minus 6 error. So it's definitely not as good as in 2D for the same bond dimension, but it's not sort of that much worse. Our rough experience is that comparable chi in 3D gives slightly worse accuracy than in 2D. OK, so that's just the most straightforward way to do things. We just do manual tensor network contractions. And we've done a few of them. And like I say, this higher order CTMRG seems to be the most efficient thing to implement. All right. Now, so the previous slides are just to say that 3D tensor network contraction is clearly feasible. Oh, my gosh, used so much time. But wait a minute, that means I have 30 minutes left. Oh, OK. Right. I thought it started at the hour mark, and I've been talking for 30 minutes. So OK, that's OK. So 3D tensor network contraction is clearly feasible. But it's clear that there's many things you can do, and you can ask if what we did was in any way optimal. They're just sort of a few strategies that we thought of in one's head by analogy to what's done in 2D. Now, in exact tensor network contraction, one knows that optimizing over the order of the contraction is absolutely essential and completely changes things from being possible to impossible. I mean, it doesn't change things just by orders of magnitude. It sort of changes things by 10 to the orders of magnitude, right? It's a really massive change. So it's an example. You can draw it from quantum circuit simulation. And this is work by Johnny Gray and Stefanos Kortis. And Stefanos is here somewhere. Actually, never met him. Oh, OK, yeah, great. I've never met you. Of course, Johnny and I talk about you all the time. All right, positive things, So this is work they did together, where they showed that by changing the order of the tensor network contraction for the sort of amplitude evaluation for the random circuit sampling, you can change things from some ridiculous numbers if you contract things very naively, right, billions of years down to orders of days, and then further work has reduced this number more. And so that's just by changing the order in which you contract things. And so you might say, well, optimizing contraction order makes a big difference for exact contraction. Can you do the same thing when you have an approximate contraction? OK, and so in principle, of course, it is possible. It's just more complicated. So there are many more choices that need to be made when you're optimizing the approximate contraction, because not only are you contracting things, you have to decide when you compress things, when you insert SVDs and approximate. So roughly speaking, the ingredients you have when you optimize the approximate contraction, you have to choose which pairs of tensors to contract. You have to choose the order in which you contract them. You have to decide where you're going to insert isometries or where you're going to compress. For example, you can insert isometries in between all these pairs. You can insert them on corners of a square, like in this TRG. You have to decide exactly how you're going to compress, because tensor networks, the compression is affected by information from the environment and how you gauge the tensor network. And then there are even more complicated things you can do, like you can rewire the tensor network and change its connectivity before you compress, and so on and so forth. Okay, so there's a large space of things to explore. So to make progress, we sort of restrict the choices that we can make a little bit. And so we rule out sort of inserting disentanglers and rewiring the tensor network as a first step. And then the second thing that we do is that we tie where you insert the compression, so where the isometries are inserted, directly to the order of contraction. And so that means that the only thing you have to optimize is the order of contraction. The order of contraction determines exactly when you compress. Now, the rule we use for compression is that we compress when the tensor that is to be contracted is too large. It gets beyond a certain size. And then we compress it before we do the contraction. This might seem not the most obvious way to do it, because you might think that you should compress whenever you do a contraction. Right? When you do a contraction, you generate tensors with more bonds, and so you should just compress them. Okay, that's a sort of ego compression. As soon as you get a big thing, you compress it. But actually, that turns out not to be very good, because as you recall, tensor network compression depends on its environment. If you compress very eagerly, then the environment of any contraction is always made of compressed tensors. In other words, it's lost some information. And so the resulting compression has a bad environment, and it actually leads to larger errors. So you should compress as late as possible. Okay, so that's what we do. We compress in this late fashion by waiting until the tensors that are undergoing contraction are themselves too large. OK, and so then, like I say, because everything is just tied to contraction order, then we just have to optimize with the contraction order, and we have to decide some metric to optimize. The nice thing would be to, for example, optimize some measure, the actual error of the contraction, but that would be very expensive, because you have to contract the tensor network to know the error, and you don't know the exact result most of the time. And so we introduce a proxy, right? So generally, we contract to minimize the maximum memory in the algorithm. If you do so, it means that if you have an algorithm that doesn't use much memory, it means you can always increase the bond dimension, right? And so that allows you, in some sense, to get to lower errors. OK, so well, how does this work? OK, so first, let's just exhaustively optimize the contraction order, which you can do in a small system. OK, so we're going to compare sort of two techniques on a 6x6 lattice. One is just ordinary boundary contraction, boundary pets, where you start from one side and go to the other side. And the other is, the contraction order you actually find by optimizing this. And you see it looks kind of weird, right? So it's not so regular. What it does is it starts from the corners, and then it contracts the corners into this zero-dimensional structure. And it actually makes a significant difference, right? So if we look at the computational resources here, which is the memory, the boundary method, as you increase the bond dimension, uses more memory, obviously gets to lower errors. But if you do this optimization to find this funny contraction order, you can greatly reduce the amount of memory used to get to the same error, right? So if you compare this error here, 10 to the minus 4, it's the same error as with the boundary method, but the memory is reduced by a factor of 100. Yes, go on.
The limit of larger networks, wouldn't it not make much of a difference if you were like reaching a fixed point? Like, isn't that more of kind of
so I'll talk about that later. Yeah, so there can still be improvements in larger networks related to when the compression is done. So typically, so asymptotically, it's true that these types of improvements from the corners don't factor into very large tensor network contractions. But I'll come to this point in a minute. Yeah. Okay. All right, and so in any case, for this small lattice, you see you can obtain a significant gains. Okay, and so as Matt was asking, one of the questions you might ask is what happens when you go to very large tensor networks? I should point out that small tensor networks are relevant in various settings. For example, if you're doing infinite algorithms, you don't necessarily need your unit cell to be infinitely large, right? But it's certainly an interesting question to ask, well, what happens with just a very large finite system? Okay, so the self-ordered contraction trees is very large, so you can't exhaustively optimize over them. So what we instead do is we do an optimization over certain classes of trees. And we just sort of choose trees to come with these different types of structures. And these trees, this is a spanning tree, for example. Literally is a spanning tree of the graph. These types of contraction trees look a little bit like boundary methods. Okay, so it's a boundary-like contraction. This is a tree that looks a little bit like an RG style thing. So it's been called agglomerative. And there's some greedy algorithm which in some ways can go between the two limits if the greedy algorithm can optimize enough. Now, each of these trees has some parameters to generate it. There's some sort of meta-parameters or hyperparameters. And so what we do is we optimize over the hyperparameters, which is essentially changing the tree structure, and then minimize the cost function with respect to these hyperparameters. And so that's why it's called hyper-optimized tensor networks. Okay. So let's now look at the contraction cost as a function of the size of the tensor network. For different types of structures. And so one has here, some regular lattices like 2D square and 3D cube, and then here this is a random regular graph, right? It just looks like a mess. And as a comparison, we have the boundary approach, which is here, the black line here. And so as a function of the size of the square, for example, this is how the cost is going up as measured by the memory, and you can see it here as well. Okay. So one finds that if one uses these different types of trees, like these different optimized contraction strategies, let's say over the greedy trees or the spanning trees, generally you will always beat the manual contraction strategy. It's particularly large for smaller systems, so that's why there's a big thing here. And one should point out that this is for a fixed bond dimension, a fixed chi. The reason why you beat at small bond dimensions is because of the use of the sort of edges and corners. If you increase chi or increase d, this small region where you get a very large advantage gets pushed further and further out, because there's more time in which you can take advantage of the edge. Then asymptotically, there's still some improvement, and asymptotically the improvement comes about really because of how we're doing the compression. So in normal boundary, you sort of compress. You create a much larger tensor network sort of everywhere, but in a d-1 dimensional space, and then you compress. And here we have a sort of slightly different compression strategy where we don't make quite as many large tensors, and this was what gives rise to the asymptotic improvement. So I think maybe that answers what your question is. Green is this agglomerative tree, which is a little bit of an RG strategy. And I won't talk about it too much here. You see that it's very bad on these regular kind of lattices, but it's the best strategy for these random graphs. And so random graphs don't have a boundary. So if you use anything that thinks there's a boundary, it's very bad.
Maybe you'll get onto this, but how does actually finding the trees scale, like these contraction trees?
Yeah, we haven't studied the formal scaling of that. Mm-hmm. We just search over let's say 5,000 instances and so on and so forth, rather than trying to find the scaling to find some optimal tree. But what you find is that if the graph gets too large, typically we find more than, let's say, 5,000 tensors, then it starts to become hard to find good trees. Yeah, but perhaps it would be OK if we ran it for longer, but we didn't test the scaling.
Excuse me, is the performance of this RG-like scheme for the random regular graph, is that related to the emergence of geometry in these regular? I don't know. I would have said it performs better just because the others are somehow extremely unsuitable, like boundary methods. But yeah, I mean, saying that actually there's some RG structure is a very deep thing. I don't really know if that's true. Yeah.
These random regular graphs just become tree-like, right, in the thermodynamic limit. Like the loop size diverges, so you could...
Yeah, but that's some really, really large number. Like the size at which people talk about that is much larger, as far as I know, than well.
Can you show that slide again? Sorry, there was a feature.
Yeah.
I mean, it seems like RRGs are pretty bad. Generally, the scaling is not approximately exponential, is Gaussian. Is that right? And the fact that all the curves are curving up.
Oh, you mean like this?
Yeah. The fact that it's outperforming it is kind of like a secondary comment.
Yeah, I mean, you don't think that in a random regular graph that you should always be able to efficiently contract it. It doesn't have any local structure, so you're expecting it to increase, right?
All right.
Yeah, well, people really care about this. Okay, go on.
So if you were to make the regular lattices periodic,
yes,
there will also not be any boundaries.
Yes.
Would you then again expect the green one?
Yeah, we did those things. No, green also doesn't work well. Yeah, it doesn't work well. Yeah. Okay, and so this is then just to show sort of accuracy versus, as a function of bond dimension. So what the previous slide is meant to show is that for a given bond dimension, the optimized strategies can give some improvement. Depending on the system size and chi and so on, the improvement may be big or small. And this slide essentially just shows that for a given bond dimension, one actually, to 0th order, gets the same accuracy. I mean, this is obviously in a log plot, so it's not, there's some spread. But very roughly, regardless of the scheme, for bond dimension 8 or 16, there isn't such a big difference. And so this sort of justifies why one is optimizing for maximum to minimize the memory, as a proxy for the error. Okay. All right. So one advantage of this approach is that you can use it to apply it to any graph. I mean, that's not really what this talk is about, but you don't have to hand code something. It just finds a good contraction strategy, and so you can. Yes, go on.
Can I just ask one more question?
Yeah.
In the first part of your talk, you said that when you were discussing the HO CTMRG,
Yeah.
you said that the boundary method doesn't work very well, and you will give some results.
Yes.
This part,
Can you use your seat mic, please?
contractions, like boundary is, I mean, in terms of efficiency, it's almost as good as the best thing, and in terms of accuracy, it's also the best.
Yeah. So right, it's a little bit complicated to discuss, right? So so here boundary doesn't do too badly. So HOC-TMRG tends to work better when the chi is bigger, and so then boundary becomes. So you should, for larger chi, it's always worse, as we find, to go from one side to the other than to go inwards one by one. Yeah. But here these scalings are for small chi. Okay, so so one could do some funny lattices, like this is Parachlor lattice, or you can do these large random regular graphs and try and solve some sort of computer science problems like dimer coverings of the which is like the entropy of the graph. And they're just computing the entropy by doing the tensor network contraction, and so on and so forth.
In the previous slide, you went up to like really large chi, like 50 or so, but then in this last slide, it was only like 10-ish.
Yeah, so the reason for that is we're trying to compare we want to compute the error, and so we have to be able to exactly contract the graph. And so these are only instances, sorry, no, these chi's are very large. But the graphs are very small because we had to exactly contract the graph. In the previous slide, that was just a scaling, and that's just the choice of parameters that was used. So you can compute the scaling for any chi, but we just use small ones there. I will show some with larger chi later. Yeah. OK. All right. And I'll just say very quickly, I mean, there have been other strategies proposed to contract arbitrary graphs. This is we're certainly not the first. So in the last few years, it's become of interest to contract tensor networks and arbitrary graphs. This is just to say that if you compare to these other strategies, this technique of optimizing over contraction patterns is clearly superior. I mean, we do more work to find the contraction pattern, but you see this is, for example, this sort of elegant scheme from Pan Zhang's group, but because they don't really find a good contraction order, so the error that you get as a function of time is, of course, significantly larger than this optimized contraction strategy. OK, all right, so that's really the second part. So this is at least one attempt to find optimal contractions. And one of the problems we encounter, which already came up in one of the questions, is if you do this for larger graphs, it's actually very hard to tell if you're doing well or not because you actually don't have a reference number for the value of the contraction. So the last part of this talk is about trying to construct some large tensor networks where you know what the contraction value is. OK, so how do I benchmark tensor network contraction on a large tensor network? Essentially, you have the following things that you need to satisfy. You need to know the exact value, of course. But then the tensor network contraction can't be too easy, because otherwise it's not really testing anything. And secondly, it also can't be impossible. Okay, so that's really the challenge. Okay, so you can find many things which don't satisfy all three, right? So if you take this norm under general unitary evolution, you know that the norm is 1. But usually this sort of quantum dynamics type circuit is usually not contractible, right? So that's not very good. Or you can take a physical model, right? And that's sort of great. Typically, the tensor network contractions are not too hard and not too easy, but the exact value is not known for the values. And then you can take more specialized tensor networks, like Gaussian tensor networks. But in some ways, those are kind of simple because like a Gaussian PEPS is sort of set up to satisfy an area law from the very beginning. So maybe it's too easy. OK, so we decided to think about sort of a different way of constructing tensor network contractions where you know the exact answer. And the starting point are these sort of corner double loop tensor networks, which came up in a different context. So some of you probably think about these types of things. So the original use of these tensor networks was to understand why the TRG scheme is not really an RG scheme. For example, if you take you construct the tensors in this way, you just make them from outer product matrices. So you take, for example, 4 matrices and stuff them in the corner of a tensor. So that's why it's called a corner double loop. And then you connect up these tensor networks, and you see they create these loop correlations. So it's something that just has short-range correlations. And at the original context in discussing this, which is not the one of interest today, is that if you apply a renormalization to this type of TRG scheme, you go through the RG process, and then you see that even though these are short-range correlations, the tensor network at the larger scale still has these loops. Okay, so it's sort of not the correct RG flow, because you'd expect that the short-range correlations should disappear. But the only property we really care about today is that this exact value is easily computable, because you can just contract the matrices around the loop and then multiply the scalars together. Okay, so the value is sort of hidden in the structure of the tensor networks. So it's important to note that these corner double loop tensor networks, although it's hard to construct the right RG theory, or one has to do special things to construct the right RG theory. Just computing the scalar value of the contraction by standard approximate tensor network contraction schemes is very easy. In particular, if you just do boundary contraction, it somehow discovers that there's this corner double loop structure immediately. So if you imagine starting from a boundary and compressing inwards and doing the standard QR, in the QR, essentially this corner double loop structure kind of comes out. And then when these are then just scalars that can be absorbed in the SVD. So with boundary methods, you can get the exact answer with a finite bond dimension. So what we'd like, so in some ways they're a little bit too easy, but what we'd like to do is to build on this structure by essentially finding an analog of corner double loop tensor networks, but where the correlation structure is not quite as easy to discover using the approximate contraction, but where there's still some loop structure so that you can exactly compute the scalar value from the very beginning. And so the proposal is to make what we call hidden loop tensor networks. And so the idea is that they're generalizations of these corner double loops, but where the loops are not local. Okay? And so you can do it in this way. So if you imagine drawing down sort of some lines schematically, then in the corner double loop case, you connect these lines on the four corners, and that leads to a local loop. But you can, of course, connect these lines at the vertices in any way. So you don't have to connect them, for example, to its immediate neighbor. You can connect them across. And if you connect them in these more generalized ways, you end up with you can end up with long loops or loops of different sizes in the ansatz. So we can make a whole class of these hidden loop tensor networks where you place the lines down, you randomly wire up at each vertex, and then you introduce, when you're wiring them up, you introduce some matrix which can have random values, for example, and this generates the state. So the contracted value is still just a product of loops. It's very easy to compute from the beginning. But the loop structure can contain lots of arbitrarily long-range correlations, so it's kind of hard to immediately discover with a tensor network contraction algorithm. OK. All right, so this allows us to extend the sort of size where we can sort of know the exact value to much larger things. So previously, so the limit of exact contraction is maybe 16 by 16, but you can certainly go to much larger things now, or even larger. And here we can sort of test out some of these different methods now on very large tensor networks, where you know the exact answer. So here I compare boundary, black again, versus HOTRG, which is a little bit punching bag, always does so poorly in these graphs. The HOCTMRG, which we described in the beginning, which is the orange, and then some optimized contraction tree, which is the spanning graph. And now you begin to see some interesting differences emerge. I mean, broadly, the sort of TRG approach is kind of bad. Things that take advantage of the boundary are better. But in fact, ordinary boundary contraction somehow becomes quite bad at large system sizes. It's not entirely clear what this is coming from, but we think it's probably because in the ordinary boundary contraction, you treat this as an MPS-MPO-like contraction across a very, very long distance. So its view of the environment is this sort of one-dimensional line that comes out. And you have non-local loops. That's probably a very non-representative environment. And so somehow the compression gets worse and worse. And then finally, one can do this in 3 dimensions. So this is some funny loop structure in 3 dimensions. And roughly speaking, these are the manual strategies at the top. And here you can start to see some bigger separation between the optimized contractions and the manual contractions at the larger chi's that one is using here in this 10 by 10 by 10 lattice. OK. So I think that's all I want to say. Okay, so the summary is that 3D tensor networks.
Can I ask you a question?
Yeah.
So in the last slide.
Yeah.
So this is this loop, hidden loop.
Yeah.
Networks that you created.
Yeah.
Do we have a sense for how well they are representing, say, ground states of local Hamiltonian? Not as an ansatz, but
yeah.
Whatever conclusions you extract from attacking these problems.
Yeah.
Do you feel confident that we should reach any conclusion about which method we should use for ground states of local Hamiltonians?
It looks like the structure of correlations that you have is a bit artificial compared to ground states.
Yeah. Right. I mean, I think these are. Yeah. So, of course, like you say, this is an artificial model. It seems to be of intermediate complexity to contract. Right. So, probably ground states are a little easier. For example, 3D icing is much easier than this. But this is much easier than contracting, something corresponding to a quantum dynamical circuit. So it's somewhere in the middle.
What I'm trying to ask more specifically is, do you have a message for people interested in getting ground states that maybe we should be looking at span or?
Yeah, I mean, what I'm intending to say, though, I don't think there's a numerical evidence, such an evidence from what I've been showing, is that indeed, using things like spanning is the way to do ground states. Yeah.
But this is not.
But this is not. Yeah. So if you apply to 3D icing, the problem is all these things are very close together, right? But 3D icing is super easy, So maybe if you had like a complicated fermionic model with some additional frustrations and becomes harder, perhaps you have this larger separation. But of course, we don't know the exact answer in that case, so it's hard to benchmark on that. Yeah.
How sensitive is it to the actual spanning tree? Like, what if you just use a naive? I don't know. You put the root in the middle.
Like if you don't optimize anything.
Some sort of, you pick up a graph library.
Yeah, so that's like how much does the optimization actually do, right, compared to? I actually don't know that. Answer. I've never seen anything.
Intuitive spanning trees for, say, a grid that you could just,
Yeah, I mean, one would say that, for example, one might think that a measure of it is the difference between, let's say, boundary PEPs, which is related to a spanning tree, and the spanning tree. So that's some order of magnitude estimate of what you get from the optimization. Yes.
Yeah.
So I'll just bring up my last. Let me just finish the talk
Yeah.
because it's the end. So I'll just say, 3D tensor networks nothing to be afraid of. That's kind of what I learned from this project. I used to think that they're really, really difficult. In 3D, this HOCTMRG is, we think, the best. Like, it's quite easy to implement, and it gives good answers. So we think is the best manual contraction strategy. Optimized contractions, I mean, you do extra work. As far as we can tell, they do improve over manual contraction strategies. Certainly on irregular lattices, they're very important, like random graphs. But even on regular lattices, you get some improvements. And especially on medium sizes where the corners, and you use large bond dimensions, where you can really take advantage of the corners, you can get several orders of magnitude improvement using these more optimal contraction strategies. And this may make sort of medium unit cells in infinite tensor networks in 3 dimensions realistic. And then finally, I mentioned these hidden loop tensor networks, which are just a new class of things that we think will be useful for benchmarking. OK.
I have a comment and a question. A comment is that it seems like in the protocol for generating these corner double line sort of generalizations of trial states, there seems to be some similarity to loop models. And so there are different complexities depending on how unbound the large loops are. So you might want to be able to deterministically create states that have different difficulty.
Yeah, so I think the difference, I'm not an expert in that area, but I mean, in loop models, usually the values of the tensors are very simple, right? And then you have a sum over superposition of many loops, like in a loop gas. But one critical thing that controls the complexity of these tensor networks is the values of the tensors themselves.
Right.
So like if they're all positive, it's really easy to contract the tensor network, right? Yeah, so here we fill them with random values between -1 and 1. Yeah.
So the other question, can I just ask? So I think my understanding is that there was this hope, I think going back to Wilson, that somehow RG helps you compute things accurately because you know how to package things scale by scale. And Migdal-Kadanoff RG never helped that. But my understanding is that when TRG was introduced, there was hope that finally we can do it. Now, what you're somehow saying is that these RG-inspired schemes, they don't really perform well? or maybe I'm
yeah, I mean,
taking
it
too
depends on
pessimistic.
what you're trying to extract, right? So TRG and its relatives have the right structure. Okay, so TRG by itself has some issues, but they're moved towards the right structure. If you want to like calculate the critical exponent, some scaling dimensions, you want to have this theory that's sort of relating things at different scales. But you know, RG is not meant to be used on a system of finite size, and in computation, you know, we are just dealing with finite size. We're not trying to always think about the thermodynamic limit. So that's why the reason why they're bad here is because I'm doing something which has an edge, basically.
Yeah, a couple more questions.
Thank you, Adam. I was thinking, you mentioned that there were positive and negative numbers, but are they complex or just real?
Oh, here we just use real numbers.
Is there a reason for that?
No, it's just like when you use complex numbers, everything's like 2 to 4 times more expensive, and you have to. There's no real reason. We haven't found that. There is a kind of phase transition in complexity depending on how positive the tensor network is. So if you make it all positive, everything's super easy. If you sort of change the range from minus 0.5 to 1, it's still easy. And the numbers are drawn from minus 0.7 to 1, it suddenly becomes hard. So there's some kind of transition in complexity there. We usually think of some like random complex number tensor networks as being difficult. And we think that if you just choose a reasonable range of real numbers, it's the same difficulty. But we haven't really tested complex numbers a lot. Yeah.
Related, you mentioned that sort of looking at a time evolution of a state and calculating the norm, that's hard. Like you said something, it's not contractible.
Yeah, if you don't know it's unitary.
Is that what you mean by that?
Yeah. If you don't know if it's unitary, and you don't take advantage of cancellation, I just said the state is I didn't know they're unitary things, and I don't have some special operations to check that they're unitary, then it's not contractible. Yeah, they're hard to contract. Yeah.
Would it be useful to benchmark against like an e to the minus beta h tensor network for free fermions? Then you know the exact answer, and maybe it's not too easy.
Yeah, that's like Gaussian type things. That's one possibility, right? They're still fairly local, so but certainly one could try that, right? And one could try, for example, Clifford circuits where you know the answer, and maybe there's some setting in which they're contractible and so on. So those are all possibilities. Yeah. Yes, go ahead.
So one way of using fermions, following the previous question, is to take a very crappy fermion to qubit mapping that will make it non-local, and then try and do it.
So, but that involves the Hamiltonians. So you mean e to the minus b to h? Yeah. We could try that. Yeah, we have not tried. That's an interesting suggestion. Yeah.
Okay, we'll do the last question over here.
You just said that if you have real and positive number, it's very easy to contract a tensor network.
Yeah.
I was a bit surprised because you can describe NP-complete problems, right? Like set and these type of things. So at some point, a random graph needs to be very hard.
Yeah. No, so I'm not making like some rigorous complexity argument. It's just empirically found that this is the case. Of course, yeah, most satisfiability things are just like things with ones and zeros in the tensor, so I completely agree with that. But I think, the statement was first made, as far as I know, in a paper by Matthew Fisher and Taryn Grover, where they just studied various positive tensor networks and just empirically found they're easy. And to our experience, if you do random values, there's probably, if one's a complexity theorist, the question is like, are random positive instances somehow easy, right? This is yeah. Well, Norb's the right person to say.
Numbers, and if you try to approximate that, it's much easier than approximating a sum of positive and negative numbers.
But is there some rigorous result with the tensor networks, with purely positive?
What tensor networks? It's just a general result in like adding up numbers, which is what a tensor network does.
Yeah.
That it's kind of much easier. It's still hard. There's an NP hardness built in, but it's still much easier to approximate a problem. You have to sum up only positive numbers. numbers.
Yeah, I mean, that's our
So
intuition
there are
as well,
reverse
right?
results on that. That's what I just wanted to comment.
Because roughly the tensor network is multiplying out to exponentially large values, and if it's positive and negative, somehow those you have the final value is if it's positive and negative may not be so large, but it's like you're summing up things that can
It
be
also
very
depends
large.
on your accuracy figure, right? If you want an absolute error, it shouldn't matter if you have positive or negative numbers. But typically you want a relative error, right? Because you have normalized expectation values. And then, of course, if you add positive and negative numbers, you need a much higher absolute accuracy for the same relative accuracy. That's maybe.
Some sort of
but it can be made. It can be made rigorous.
Some sort of sign problem.
Yeah, I guess it's linked.
It is like an analog or sign problem. Yeah.